Alright, draft physics video presentation. Yeah. Alright, well, comments, which are just, the troll shows up, the cowboy, a bunch of different accounts, blah, blah, blah. But we'll go through some of it just because it's just so stupid, and it just illustrates the point that he's crazy. That this really doesn't have any agenda behind it at all. Rational one. He's just a kook. And set free on us, unfortunately. We don't have any kook asylums. So anyway, so then he says, do you actually think it makes sense to make train compartments that tip over? Sure. You fill them up with something and then they tip over and they spill all the stuff out. Sure, yeah, it makes sense to me. Anyway, how does that even work technically? You just put it on a hinge, it just rotates. Not a real big problem. Come on, they only weigh 65 pounds or so. Yes, at the end, that's what they weighed. So that was part of the German strategy, was to starve them to death slowly, and then kill them. That was part of their fun or something. So whatever. So anyway, this all has to do with, look, I find a few details of the story of the Holocaust to be a little bit implausible. It's a fact. Okay, there's no denying that millions of Jews were killed, and they were killed because they were Jewish and because the Nazis decided being a bad person or a nasty person was somehow genetically a Jewish quality, and therefore Jews were just a menace because they were genetically menacing, some kind of horse shit like that. And I clearly stating that's horse shit. That's really stupid. And wrong and evil and all that kind of crap. I just don't believe the evil was implemented exactly how they say in the little storybooks. Fine. Call me whatever you want, any kind of name, but I don't think what you can call me is anti-Semitic, because it really doesn't have anything to do with any feeling or thought connected to whatever race the Nazis happened to be killing. But anyway. So, just stupid comments. So, did you hear the one about the Jew doing the backstroke? So, this guy is supposed to be somebody who's upset because I've said something out of line against the storybooks, and against their historical fables, and because I'm not complying with saying exactly what they want me to say. I've offended their religion and their heritage and their whatever, blah, 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 and they have some right to fight back with lies. Because somehow I'm being insincere. I'm lying, that somehow I really do believe it happened that way and I just don't want to admit it, or some kind of horse shit like that. And then he tells a cliche Jew joke. So this is a guy defending the conventional story of what the Holocaust was and why it happened, and that you can't disagree with because it's a sacred story, and yet he's making jokes. So you think that's going to make sense to a judge? See, a judge might have had sympathy for you if he found you to be some sort of a religious fanatic, in defense of, then you're all acting out of defensiveness, like you had some real trauma, some real post-traumatic stress syndrome thingy, some kind of real excuse for being a little bit out of line. He cut you some slack, but this is just showing that this has nothing to do with any of that crap. That you're being totally insincere in saying you're fighting for God, or you're fighting for defending your people, doing any of that. You just lost all credibility. You're just demonstrating that you're the anti-Semite. You're just playing this game with words to slander other people, because it works. So you so lose. You're just such an idiot. And he calls himself LOL suit, right? So again, a judge is going to find it a little bit disingenuous that somebody actually points out to you that I've sued people before, that I've gone to the trouble, the expense, the aggravation, the irritation, to spend years, working the system to try to get my little piece of justice. And so somebody warns you that they've done it before, that you're doing exactly the same thing as the last guy did. So why wouldn't I do it if I have to? And you're laughing at it. You're laughing at the whole idea that you're saying you're above the law and you're above worrying about it. When that's kind of silly. You should have show some respect for the law. And you're not showing any respect. You're not showing any respect for any rational restraint. You are just a fucking internet terrorist, and that's it. You're just demonstrating that's all you intend to be. Okay, is to sit there and cheat the system wherever you can. You're cheating YouTube's policies to create all these fake accounts. You're just, showing you just don't care about rules and regulations. You don't care about civilization and civilized rules of conduct. You're just showing it right here. You're proving the case for me, you moron. Thank you. Thank you for making my eventual effort to show you what justice is that much easier. Okay. I mean, you really are helping so much. Appreciate it. So I'll block them in a minute once I get through all of this crap. But this is the comments you get. What the fuck is this? Finish the sentence. Moon Man's been smooth since days of spilling juice. I don't even know what the fuck that could possibly mean to anyone. Hilarious. Alright, and the last of his comments is somebody says, religion without quantum physics is an incomplete picture of reality. Dalai Lama. I mean, at least he's being honest enough to call the Dalai Lama, it's a religion. So anyway, tell that to the international bankers. So another shot at the Jews. Okay. So I think that's the end of that crap. So we'll just get rid of these fellows. And be done with that. That comment's okay. These are all nonsense and garbage. Sorry, I mean, I should have just blocked this stuff, but I mean, there's a point to saying it publicly just to recognize the argument that's been made and the context and how this is really stupid. Talk about crimes against humanity and make a joke. It just shows no appreciation for even the whole concept of crimes against humanity. Yeah. Just too stupid. Alright, so I think we've got everybody now at least once. Alright. I watched some of your videos. A lot of opinions, but zero experimental data or math. So it doesn't make any sense, right? I mean, you play Professor Lewin's, 70 of Professor Lewin's videos, maybe. I don't know, at least 40. Okay. So at least 40 complete lectures in my videos. All right, plus all the other, context of the other descriptions of experiments, demonstrations of experiments, all of that content. Just pretend it doesn't exist. Is that what you're doing? You're just pretending it doesn't exist? It doesn't make any sense. And clearly the math is, what math is reasonably discussable. I mean, some math isn't even, you can't talk about it because it's so convoluted. But the math that's within grasp, I mean, F equals ma, and the basic, I pointed out about how the gravity math is sort of missing the point, that it's not one force. When two things are interacting with each other, there's actually both of them are producing gravity. It's kind of silly to talk about it as one force, as a net force, when the individual forces should be understood as individual forces. Individual changes to the environment. You can win all these semantic arguments. It's semantics, whether or not it's a wave or a particle. I don't think those are semantical terms. And jump on the pros for trying to dumb it down. So he thinks the pros get it wrong on purpose, because they're trying to dumb it down. They're not themselves making mistakes. So it's not possible that they don't know that the detector experiment was never done. are, you know, I mean, and then how do you dumb down some of the questions that have to be asked about the theory behind things? Like, you actually believe there's some good reason that light is twice as bent by gravity. And you believe there's some good reasoning that could be applied to explain how LIGO can send a beam into mirrors 1,600 times and know exactly how far each photon went into the mirror. You think that theoretically can be made to be understood? Yeah, no, I don't think so. Dumbed down for the masses. No, so it's not dumbed down, it's recreated. As I stated, they quote mine the experiments and show them one way only, to make an argument. As I pointed out, the geometry, the math, is exactly the same for jamming in the radar experiment. Jamming explains the phenomenon with exactly the same mathematical construct. And you don't, so the simple argument is, how do you know it's interference when jamming does exactly the same thing? All right. But in the end, the data and the math is validation. So again, says you. I'd say the math in the two-slit experiment is overtly incorrect when it comes to the double slit. It's not predicting the right pattern. Now, that's an overt statement that you could refute with some sort of evidence. The math that works has the surfaces as the point sources. Do you understand that? The math that actually predicts the two-slit experiment, the actual pattern, that math, all right, doesn't have two waves in it. It has 4 point sources in it. How do you explain how that's wave affirmative? That's proving, that's validating wave theory. So you're creating point sources that aren't, again, understand, it's not, I could re-show the image from the mathematical paper, but I mean, do I really need to? The math that works, all right, considers these the point sources. So when they do the path length difference math, all right, the path length difference is here and here. So these 2 points create the big pattern, and these 2 points create the small pattern in here. Okay, now that's the facts. Okay, so, and you're saying that those facts validate waves. That means the wave has to be here, and the other wave has to be here, and the wave has to be here, and the wave has to be here. And even that won't work, right? I mean, it won't work in the sense that if you actually did the experiment with, if you actually did the experiment with, if you could actually put waves in this sequence, then you'd get the pattern. But how can you construct waves in that sequence? How can you have the waves going, initiating over the surfaces? You see, the surfaces are here. Now you have your waves. How can they do that? Waves don't do that in the real world. So how is it validation? How is the math that works doing this validate some notion, okay, some young notion that 2 waves are coming out of the 2 slits, and that's all there are. 1, 2. How does this fact validate that theory? Oh, that's right, it doesn't. Dumb it down for the masses. All right, the math is validation. By the way, tensor algebra is not horseshit, says you. Okay, I mean, it's not horseshit in the sense it's just another example of statistics. So I mean, tensor math has to do with again, it's what's the word they use for the, you're taking a big complex system and reducing it to some complex, simplex outcome. So you're taking a system of a plane that has a bunch of lumps in it, a lump here and a lump here and a lump here and a lump here, and you're trying to figure out a way to measure how much all these lumps add up to, and what the overall thing would look like if you spread those lumps over the entire surface or something. I mean, that's all it is. It's just, but it's a complicated thing to do, to take a bunch of a bunch of different, unsystematic things that are happening on a surface and turn it into an average that you could understand. But anyway, in 3 dimensions. All right. Horseshit. Take a course and then point out its flaws, please. Well, I'm not going to do that. So, frankly. You waste your neurons your way, the way you choose to waste them. I'll waste my neurons the way I choose to waste them. Thank you very much. Alright, so this is the troll. Tensor calculus is like all things half-baked, needs to go back in the oven. Yeah, well, whatever. So we'll just remove that since I've answered it satisfactorily. Alright, so, Dino. In your theory of gravity, what accounts for the perception of weight? Okay, so I should have said that in that their analogy of gravity is flawed fundamentally, right? So we're using this comparison between somebody standing on Earth and then somebody in a rocket ship, and I should have. Oh, fuck. Well, I do have a smaller piece that I can use. All right, so you have the thought experiment. So you're in a rocket ship, okay, being accelerated, and so and then you're standing on Earth, where gravity is doing the acceleration. The trick is, okay, the rocket only has one force source, so it's one force acting on the rocket. And obviously, okay, you're going to feel it because the rocket pushes your feet, and then your feet have to push your legs, and the force has to move through you. So it's like the difference between me shooting a bullet at a surface, and then me. The analogy I'm using, shooting a lot of little tiny atoms at you, okay, spread over your entire, that went in different depths inside of you and all that kind of stuff. So it's all about how you spread the pressure. Gravity spreads the pressure with a bunch of little tiny bullets with little tiny bits of energy that hit all of the atoms, okay, where the bullet just hits all the energy in one place and bores a hole right through you. So the two forces will act on you very differently. Now, when you're on the Earth, you're not doing just one force. Gravity's doing this. And the force you feel is the Earth doing this. That's the one you're feeling. You're not going, you've got zero velocity. See, this thing is moving. So this thing's accelerating and it's going, something, miles per hour. Okay, it's moving. This thing isn't moving. Okay, so obviously gravity's being countered by a force inside the Earth, pressure, chemical pressure. And the chemical pressure is pushing you back up. So you're feeling the opposite force, the Earth fighting back. The Earth saying, I'm already full of matter. I don't want any more. And it's rejecting the matter, okay, and it's pushing it back. And so you're feeling it like this force, you're feeling your acceleration at your feet, but the force that actually initiated it is this down force. If it wasn't for this down force, you wouldn't be feeling any pressure force from the Earth saying, I don't want to eat you. I don't got room for you inside of me. Okay, no room in the inn. Get the hell out of here. So there's two forces involved in this scenario, when there's only one force here. So that's why the comparison doesn't really work, because it's not the same circumstance and you're not moving. You are moving is the argument, okay? It's just that you're doing this, okay? Gravity's pushing you down, the Earth is pushing you back up. So you're moving this whole long distance. So in a sense, your velocity this way is going to be very fast, because like a basketball, you're bouncing up and down the whole time. And that's why your clock here on the ground is the one going slower. okay, than the one in space. It's because you're the one going much faster than the satellite, technically, because you're bouncing in a lot more gravity. We've been over this, but it's good to go over it again, I guess. Good to be clear. So I hope that clarified for you. So anyway, I'll go through the rest of it. Okay, perception of weight on the surface of a massive object. How does a more massive object like a planet, for example, seem to have more gravity than a less massive object like the moon? Well, again, how much gravity it has to do with how much energy it's stored. Storing energy, storing movement, how much movement there is inside of it. Okay, so again, the argument is that stuff has to be moving to absorb the force. You know, that's how you move. And that if your atoms are moving, they have to be absorbing a force. A force has to be doing the moving. It has to be occupied. So let's say the matter moves half the speed of the force. So if a piece of force hits an electron and it's going the speed of light, c, well, let's say it'll move the electron, half the speed of c, and it stays there. So now the force that was going this way, the speed of light, is now only going 1/2 the speed of light while it's stuck on that piece of matter, moving the matter from this location to this location. Alright, so you can understand that this has absorbed something that would be called energy, in the sense that you've taken half the momentum out of the photon by occupying it moving a piece of matter. So the idea is that inside the Earth and all the big things that get gravitational, it's happening in the little ones, but you can't measure it because it's such a little bit. So the Earth is all molten inside. Inside here it's all molten, and there's stuff moving this way and there's stuff moving this way, and that's why it's molten. It's because it's moving. So you could say it's swirling in a circle. It doesn't really matter. But the point is it's moving. And as it's moving, that means force that was going this way and force that was going this way got used to cause that motion. And so that force doesn't get where it's going. And the net situation is that there's a lot of energy being absorbed. So everywhere around here, no matter where I put a looker, something that's going to look at the Earth and say, what does it look like? Well, they're going to see the fact that they're not getting hit by this force, right? This force got used up in here, so it didn't get to here. They'll see that. Now, the force that got used up going this way, right? So the one invisible over it going this way, this guy can't see that one getting used up. So it only sees the force getting used up going one part of the circle. The other half of the circle it doesn't see. So even though there's equilibrium here, it's not equilibrium in terms of its perception. It only sees force. I can't see, say I'm blind, I don't have vision. I can feel a baseball hitting me. I can't feel when I throw one and it hits somebody else. I can't tell that happened. So I'm going to notice when stuff doesn't get to me, but I'm not going to notice that the stuff that I'm radiating didn't get to somebody else. I can't notice that for them. So there's going to be an equality. So again, if I put this other object directly across, you can sort of understand that this one sees the force get absorbed this way, and this object sees force that gets absorbed this way, but they can't do the opposite. So they can't tell. So from every perspective, it's going to look like I'm getting hit by less. That means the external pressure is going to push me in, right? So all of these are going to get affected by the external pressure that's going to be pushing them this way. They're getting less pressure this way. So obviously they're going to move in a net direction of that way. And when they move, they're absorbing force again, right? So now they're creating less force hitting the other object, and the other object's going to tend to move that way eventually. But obviously when you're talking about a human being versus a giant planet, the amount of the planet moving is so slight, that it's barely, we couldn't even measure it with instruments in terms of the Earth's total gravity. It wouldn't be a detectable change. Would be, point, 1 times 10 to the minus 40 or 50 or some other stupid crazy number. In terms of the percentage of the Earth's mass, it's a tiny percentage of the Earth's overall mass. So anyway, so the Earth already has gravity before we even show up. So if we're over here, the Earth has already been doing this stuff. It has a whole bunch of matter moving in, okay, and moving out. All right, so it's doing this bouncing thing. All the pieces of mass inside of it are moving in both directions, all directions essentially over time. And by that process, from everybody's point of view, it's going to look like they're getting hit by less. Period. Because they can't see the opposite happening. So there's just a bunch of matter moving. When matter moves, it uses force. When it uses the force doesn't get where it's going at the speed of light anymore. And that's all you need to create this effect. And it's clearly proportional to how much mass you have. The more mass you have that you're moving, the more little electrons and protons that are moving somewhere, the more force that isn't getting where it should have been going, and i.e. gravity. Alright, like a planet, for example, seemed to have more gravity the more mass of the object. Right, so the gravity is completely, you can only absorb say it's a rain in the universe is raining, and I was just to use one dimension for this purpose, and I stuck something in it. Only so much rain is going to hit something this size, and more rain will hit it. The bigger it is, the more rain will hit it. And obviously we're talking about it's every bit of it, okay? The rain gets through it and hits all the little bits inside of it, so you have to think one step further to the smallest bits. The atoms, the electrons and the protons are the rain catchers, and obviously the more electrons and protons you have, the more rain you catch. So that's why the force is completely proportional to mass. I've heard you touch on this subject before, but I'm still a bit confused about how the pressure effect works on the interior of objects. So pressure is just about interactions and proximity. So the closer two things are to each other, the more energy that can possibly reflect back and forth between them. And that means more interactions with surfaces. So the further two things are away from each other, the fewer interactions that take place on the object. So the total universe is affecting something with a bunch of energy. The closer two things are, the more parts of the universe that are affecting them more often because of reflections. And so you're going to kind of understand that proximity is pressure. Well, it automatically happens as soon as you bring matter close together, and how it makes things seem heavier or lighter on the surface of that large object. Well, it's not just the surface. Like I said, all the matter below you, is under pressure. It's all pressurized. The deeper you go, the more pressure there is. So the more compact things are getting, the more irritable they get in terms of the energy that's getting trapped between them. So the hotter they get. Alright, any chance you'd be willing to slow walk through those details one more time for us slow kids in the back of the class? Well, you're probably just, smoking roaches back there. Anyway, the force bits are sleeping. That's what I did in the back of the class. I went to sleep. The force bits compress the celestial object a bit like a gas. Anything on the surface of the Earth is affected by it as long as it is 65 pounds. So that's the troll again. Yeah. So again, is the Nazis were clever in the sense that they didn't just shoot the Jews. No, they had this master plan of killing them really, really hard and slow for the fun of it. The more expensive way. They didn't care about money. They had so much fucking money. They didn't care how much. Yeah. Let's kill the Jews a really expensive way. because they had a ton of money and they just didn't care about. We don't need any more tanks. We don't need any more, shiny uniforms. Let's just throw the money away, killing our enemy in a preposterously slow manner. I really don't want to have a Holocaust argument. Fine. Yeah, I'm just saying. Here he is sitting there asking for the conversation. So he's clearly not afraid of it. He clearly doesn't want to hear alternative speculation. So I'm just doing this for the point of showing this is supposed to be a guy who has an agenda, and his agenda is completely insincere. Let's see. Mac tonight, you went with that comment. Okay, so like I said, this is all one person. Obviously, two trolls with silly names don't show up at the same time. So this is obviously the cowboy. Anyway, talking to himself. Psychotic kook. Let's just do some more removing. Alright. So incoherent magnetism. So this is the whatever this is. Incoherent magnetism ? I'm just saying I wouldn't use the word incoherent, because it's not the same thing as chaotic or, well, in a way it is. I just don't know if it's the right way to say it. It's no longer magnetism is the point. Okay, the iron atom is naturally, when you put a group of them together, so you have a piece of iron that's not magnetic. You don't call it incoherent magnetism, right? I don't think there would be any sense to it. But you know that the atoms all have an alignment, a plus and a minus, a north and a south, we'll use for the sake of argument. That the atoms themselves are little magnets. And you know that, okay, they're all aligned in all directions. So obviously there's no coherent magnetism because they're all aligned in different directions. So if you thought of north and south as red and blue, okay, you'd understand that, the only thing somebody's going to see out here is purple. All right, so that's not quite good enough. Right? So yes, so you could say, yes, the piece of iron has incoherent magnetism, when it's not a magnet. Well, you could say it, but I don't think it means much. So that's all I was saying. I just don't think it's the best way to use the word. But whatever. Like magnetous ball bearing, in line they are coherent magnet. Bunched in a sphere, they are incoherent magnetism. Well, I don't know if that's exactly true either. I mean, even when I put a bunch of round balls in that are magnetic together, they tend to want to line up. So they will line up sort of like an Earth. You know what I'm saying? They'll tend to be a north end and a south end, but it's going to be weakened because there's going to be a lot of alignments that aren't perfectly straight. They're going to do a lot of this kind of thing. So these clearly, the ones going this way will be in conflict with ones going this way and screw up the magnetism. So it'll be a weaker magnet, but I don't think it'll be no magnet. So I don't even think that's correct. Let's see. Bunch of sphere, they are incoherent magnetism. That's not good. These might be other possibilities since we did not play with geometry. I don't know. I think it's fundamental to understanding magnetism is some geometry. If you put the centurant magnet on a bar magnet close to an incoherent magnet, literally nothing happens. If you put I don't know what this is, close to an incoherent magnet. So again, but the incoherent magnetism you're saying has to be permanent magnet. So you're saying you have a permanent magnet. I mean, they can do this. They do this to make refrigerator magnets and stuff. Some of the magnetism is deliberately in different directions. to create, a side that's more magnetic than the other side. Okay, so they can create inconsistent polarization by doing some tricks with north and south and north and south. So there's certain arrangements of it that create a magnet that's only magnetic on one side. But clearly that's not incoherent at all. But if I make a permanent magnet that's permanently incoherent, then it's like stainless steel, right? Like real stainless steel is basically not produced in a magnetic field, is a bunch of alignments of domains, and they're hardened, so they won't move again. So even if I hit the steel with metal, I can't. They're very rigid. That's why stainless steel is so hard, and it's because it's made to be that way. Everything's frozen. So it's permanently unmagnetizable, even though it has the little iron elements in it. The iron elements can't turn, and if they can't turn, they can't, reinforce each other's direction and strengthen the filtering effect. The filter is broken permanently. So yeah, bringing a permanent magnet towards a piece of stainless steel, real stainless steel, isn't going to work. Isn't going to make the stainless steel magnetic. But any other piece of iron, any softer piece of iron, it will work, and it'll become magnetic. So this isn't complicated. Anyway, literally nothing happens. Something should happen. It does not. So again, you said something should happen. It will happen if the iron atoms can move. If it's soft iron, the iron atoms will move. They'll complement the permanent magnetism and become opposite magnets, and it happens. They demonstrate that all the time. So anyway, you ain't thinking quite right. Okay, you're kind of not off the subject, but there is nothing to do with this capital letters. It does not. That's not the truth. Alright, so we'll just remove it. It's semi-obnoxious, but whatever. Alright, so I think that's all we need to mess with at this time. So we can move on to some quantum crap, I suppose. Where they start talking about entanglement and other bullshit. So I figure I can do a little bit on that. So maybe I'll take a break first. Have a drink. Yeah, first. You need something to take the edge off. Anyway, I'll be back. Alright, I think I found the courage to endeavor to persevere. So leave us begin.
If they align with the probability profile given by this wave, whose equation we showed you, and that is what works out the shape of the wave in any given situation.
So let's understand, they have no equation that predicts anything. The equations are basically just statistical tools, a way of analyzing statistical data. So you have to put into the experiment all the variables and all, into the formula. And it's just telling you what the variables mean, like, velocity plus mass equals momentum, or some kind of simple argument like that. You have to put the numbers in to get anything out of the equation. It doesn't predict what the thing is doing. You have to tell it what it's doing. You have to tell it the odds, essentially, before it predicts anything like the outcome.
And just to bring this full circle, if we look at the double slit experiment, in this wave-like language. Now think of the electron or the photon as a wave. It goes through, it interferes like water waves going through the two openings. And
so it doesn't do anything like that, right? So again, this is so dishonest to the actual pattern created in photons. There's clearly two patterns. Clearly they're ignoring that fact. This is a 2017. In 2017, everybody who knows anything about physics knows the double slit pattern is a much more complex pattern, and there's more for you to explain. It's not doing some simple little, there's some bars over there. So people are arguing that they're doing this gross simplification to shore up their theory, or to make it understandable. well, how is it not completely dishonest, though, to pretend that that's what you have to explain? And the truth is the pieces that are missing, the part that he's ignoring, isn't some part they have any way of explaining with that wave picture. That wave picture won't explain the real pattern. So again, understand the real pattern. Okay, the real pattern, is this. Okay, there are two waves can't do this. There are two waves can do this, and so that's all they're showing you. Okay, but their two waves can't do this other pattern, the secondary pattern. No way, no explanation, no way you can do it. Two waves can't do it. Four waves can do it. 4 point sources can do it. 2 point sources can't. Fact. And so they say they left this fact out because it's superfluous and unimportant and uninteresting. No. They left it out because their theory doesn't predict it. They have no explanation for it. Their theory doesn't fit. It doesn't fit the evidence. It doesn't fit the outcome. And they're just quote mining reality, and they're doing it. And it's not even a quote mine of reality. They're overtly cheating the truth. They're not just leaving something out. They're cheating.
Therefore, you have an interference pattern on the screen, which is telling you where it's bright, it's very likely that you'll find the particles. Where it's dark, it's unlikely. Where it's black, there's zero chance of finding the particle there. And therefore, you run this experiment with a lot of particles, and they're going to primarily land in the bright regions. They're going to land somewhat in the grayer regions. They're not going to land at all in the black regions. And indeed, that's exactly...
So that's not either the truth either. They're not going to land at all in the black regions. That's the whole argument here, is that some of these black regions aren't entirely black. Okay, it's not, all or nothing. That there are noise photons that do get in here. Okay, they're just much lighter and, less intense. And all you're really doing is increasing this intensity. So when you increase this intensity 4 times, obviously you make whatever was here look like a lot less light.
See what we showed in the experiment that we ran with the double slit just a moment ago, and that's why we believe these ideas. So that's, in some sense, really the...
So when they ran it, right, they showed you 4 blobs of light, 4 little circles, and said, see, look, double slit pattern. And we're supposed to say that, oh yeah, that's just cheating to help the audience understand. No, that's cheating to rationalize a theory that really doesn't work.
The basics of quantum mechanics. Classical physics, particle motion is the intuitive one described by trajectories. In quantum physics, the particle motion is somewhat fuzzier. It's got this probabilistic wave-like character, and the
this notion of Heisenberg, this idea that something isn't in a location, so that's the big difference from classical physics. None of the classical, Newton and his friends, none of them anticipated that you could get away with saying, well, the particle doesn't know exactly. The stuff isn't really in a place in space. It's in more than one place at the same time. It's just, it's a ghost, and then it turns into a real thing. And, it's the invisible man, and he can be everywhere or something, and then he drinks a special formula, and that makes him visible. Or, it's just a wacky story.
Curious thing about a wave, it's sort of a wave of probability. If the wave is spread out, it means there's a chance the particle's here, a chance that it's here, a chance that it's here, and therefore...
And it only lands in one place, though. And it does so by predictable variable circumstances. So I change the variable, I change the width of the slit, I change the probability. Well, gee, maybe the surfaces have something to do with it then. If I change where the surface is, I change what happens. Well, that sort of makes sense in a classical sense.
Where the wave embraces a whole distinct collection of possibilities all at once. That, in some sense, is really the weirdness of quantum mechanics.
The silliness of it. From, depending on how you want to use language, that's silly. It's not just weird, it's silly.
So that's the basic structure.
The simple answers do work. The simple mechanical explanations can be found. Like in the radar experiment, jamming. Same math, same geometry, same path length differences, all of that crap, just a different reasoning, and pointing out that, well, we can only detect radio waves that aren't jammed. You know, we can't detect them when they're jammed.
And now we're going to move on to our next chapter where we're going to dig a little bit deeper. We'll talk about measurement and also entanglement. And we can get this guy going here with a...
And it's a dead heat. They're checking the electron microscope, and the winner is number 3 in a quantum finish.
No fair! You change the outcome by measuring it.
All right. Now, either we have a very sophisticated audience or you just love Futurama. I'm not sure which. But this is part of the issue that we now want to turn to, which is if you have a quantum setup, how do you move from this probabilistic mathematics saying that the
how do you move to understanding all of these interactions as real interactions? Because this whole quantum thing gets a little bit screwed up, right? I mean, this whole idea, okay, let's say this thing, okay, there's a thing, and we're saying it's a probability wave, so it could be here, it could be here, it could be here, it can be in all of these places. Well, the thing that I'm going to interact with is doing the same thing, right? So it's supposed to be a bunch of, well, I'm probabilistic too. The photon I'm sending to look at this thing, this electron, so they're both in this unstable state of not having a real place. So which non-real entity here is going to interact with what real non-entity here? Okay, so every measurement is already a quantum event, and so you can't, theoretically, there's no standard by which anything could be understood because there's nothing solid in this whole equation. There's no, I can't collapse this one's wave function ahead of collapsing this one's wave function. So I have two wave functions interfering with each other, interacting with each other, and there's no coherent or rational way to ever be able to say I can know probabilistically what's going to happen because both of these probabilities are completely dependent on this being stable. If one of these two items aren't stable, I can't have any probability. I can't do any math. I can't do anything. So how can they have any rational physics when they can't ever have a rational measurement? No measurement can ever mean anything because they're two different quantum states that are affecting the measurement. The ruler's changing as much as the damn thing you're supposed to be measuring. It doesn't make any sense. How could you ever say something ever was an outcome? So you're back to many, infinite universes because everything has to happen. Every combination of this possibility has to be combined with every combination of this possibility and multiplied into all the permutations. So yes, you create 768,000 universes because you shot a photon at an electron. I mean, what a pile of crap.
electrons, say, could be here or here or here with different probabilities, to the definite reality that Mark was describing. When you actually do an experiment, you find the electron here or here or here. You never find anything, a mixture of results.
So, yeah, but you didn't find it here, here, or here based on where it was, because your measuring device changed where it was. So what's the difference? You didn't measure it where it was. You measured it where your collapsing of the wave function happened to be based on what you sent into it. So it never was really there. It never would have been there because you hit it with a bunch of probabilities, extra probabilities. Ones beyond the probabilities it had, you added more probabilities by measuring it.
We want to talk about how we navigate going from the fuzzy probabilistic mathematical description to the single definite reality of everyday experience. And this is something that many physicists have contributed to over the years. Again, Niels Bohr, we had a quote from him early on.
So let's understand that this is the place where physics shows how it's totally schizophrenic and irrational, because 1/3 of the physics people will say that didn't happen. You know, 1/3 will say yes, infinite number. Not infinite. An insanely numerous number of universes is being created every millisecond, and in each one of them, all these wacky combinations are realized.
And he's certainly viewed as really one of the founding pioneers of the subject. But let's now try to go a little bit further with our understanding of going from the math to reality. And we're going to follow in for this part of the program, really in Niels Bohr's footsteps in something called the Copenhagen approach to quantum physics.
So this is something only 1/3 of the physicists believe, or maybe a tiny bit more than that, 40%. The other 60% believe some other kind of crazy nonsense. And this is what they're asserting is the truth. So even though they can't agree on this truth, but they're perfectly comfortable with it, saying that we know. So even though they obviously don't know, because they all will have different opinions, they're saying we agree. They're saying to you, this is something you should believe because, yeah, we've tied up these knots and we've made this all clear. And yet they have completely divergent opinions about what's actually happening. Just doesn't make any sense how they can sell, we're sure it's one of these three things. Is that it? We're sure it's one of these three. Yeah, maybe it's not any of these three.
Can you just begin to take us through what was the ideas of collapse of the wave function in technical language? What are those ideas all about?
So look at it this way. I've got my probability wave, which is sort of humped, let's say just for one particle. It's humped over here, and it's humped.
Yeah, so again, this idea that because we can't see it, we're going to assume it's a wave of probability. So instead of just calling it what it is, a thing that we can't see, we're going to say it could be here, it could be there. No, it's everywhere. It's all the places it could be. Why would I do that?
Over here. So there's kind of two ways I could think about that. You might say there's an and way and an or way. So I could think of it as saying that the particle is here and the particle is here. Or you could think of it as saying, well, the particle is here or the particle is here. And the problem is I kind of need to use both to make sense of quantum mechanics, or so it seems. So if I try to explain the two-slit experiment, I have to think in the and way to start with. I have to think the particle's going through this slit and it's going through this slit.
So again, this makes no sense, right? I have to. He says I have to. When they know, okay, they know. So first off, so for the people who say they're just cheating for the dumbos in the audience, clearly you're saying that the physicists don't know these truths about how the pattern's created. So this idea that they're saying, oh, well, there's two openings, and I have to assume that the same particle had to go through both, so it could have some interaction with itself, and cause some effect. When they know the single slit does the same goddamn thing. That a single thing goes in, okay, and somehow two wave functions come out. And the two wave functions interfere with each other and cause the outcome. So you already know a single slit creates two wave functions. So why are we having this conversation? That doesn't make any sense. Clearly, the thing doesn't need to go through both slits to create two wave functions when it can create two wave functions just by going through one slit. So this is completely demonstrated to be an unsound argument to be making, that somehow the particle needs the two-ness here, that this two-ness is really important to making two waves. When you made two waves over here, with a single slit, you made the two waves. So, where's that? Is there any continuity here? No, there's no continuity. And then again, the math that works has four waves. Okay, so let's just point out again. The math that works has four waves, 4 point sources. All right, and that's really what's happening in the two slit. That explains the real pattern. Blah 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 blah. So this doesn't make any sense. There's no, like I said, the Young experiment is debunked. The Young experiment doesn't create the actual two-slitted pattern. You can't do it with two waves. You can't take two waves and make the complex pattern of little bars. You can't do it with two waves. Oh. Well, my bad. Okay, gotta move the camera over a little bit more. Something like that. So you can't do it. You can't create this, okay, with two waves. Doesn't work. So none of this theory has any real connection to the actual real world. So this whole idea of the photon having to go through both slits to interfere with itself, again, is this notion that they can create a single photon. They've actually done these experiments. They actually haven't done them in any kind of clinical way, any kind of careful way, where they're sure it's only one photon at a time going through the slits and you still get the pattern. Hasn't been done. They can't show you the video of it because it hasn't been done right.
It's just going through this slit, or it's going through this slit. I could close one of the slits and it wouldn't make a difference. But then as soon as I look where the particle is, suddenly the and way of talking stops making sense, because it doesn't seem, we'll come back to this, but it doesn't seem...
All right, so again, he says, as soon as I look at the which way, we already know that you can't do that. There's no theoretical way to look at a photon. There's no theoretical way to even look at an electron. They are invisible to our technology. They are, in fact, invisible. You can only look at them by completely disrupting. You know, you have to push them into something. You have to smash them. You have to do something to them that's quite catastrophic. You cannot possibly passively look at an electron or a photon. So the whole concept of him saying it as if we've done the experiment and, oh, every time we looked at one of them, they did something different. They have no experiment. It didn't happen. It can't happen. They're making this up, and they're getting away with it. And everybody's applauding and saying, boy, your physics is so, wow, that's such a rock-solid argument. You've really proven it. With what? A misdescription of reality. The proof is entirely made up. Well, entirely. Most of it.
seem is if I see the particle here and the particle here. It seems as if now I need the or way of thinking. So what came out of the ideas of Bohr and Heisenberg and Dirac and people in the 20s and 30s was, well, there must be some new bit of physics, some way in which that Schrödinger equation we saw earlier isn't the whole story. So suddenly the wave function stops being peaked here, and it jumps, it collapses.
So let's see a quick picture of that collapse. So if we have a probability wave here, and this is the and description.
So again, he's saying this is a thing, okay? Like this could be a human being. This is what you are. You're a wave of probability. Yeah, a car, a tennis ball, a baseball, the moon. It doesn't matter what it is. It's somehow this thing. It's not made of stuff that's in a position. No, it's some sort of this mush.
In your language, it could be in these variety of different locations, and I now undertake a measurement, and I take that measurement, and it collapses to the or way. It's only at one of those particular locations.
Right. So, and again, I collapse it with something that doesn't collapse it reliably. So I don't know how it's going to collapse it. It could collapse it by clearly still influencing it. So the collapser is going to clearly change it because it's also in a quantum state of waving.
The wave function is gone.
And if I turn away and I'm stopped measuring, it melts back into the probabilistic description. And
all right, so he stops measuring. So again, this whole idea of these measurement experiments never happened, theoretically impossible. Just even doing the electron 2 slit is theoretically impossible in the same circumstances. I mean, clearly the light's polarization is critical to the pattern you're getting from the single slit. You change the frequency of the light, you change where the pattern is for very good reasons. And so clearly it's a factor. Electrons don't have any polarization. It's a silly notion. You want to give them a fake wavelength, well, that's your business, but you can't give them a fake polarization. So there's no way you can make a slit that's actually confining to an electron. Electrons are a million billion miles from their perspective away from the from the proton that's attaching them to an atom. How the hell could you possibly create a slit small enough where an electron's going to feel trapped?
we're back to a language that feels quite unfamiliar, where the particle is in some sense at all of these locations simultaneously. Now, the issue that you raised is you said, look, we're going to have some other math to make this happen. So
the or argument would be the more rational argument. We just don't know. The particle is in one of these, it's in a location. We don't know exactly where it is. We can't measure it, but we can say what the realm of realistic is for where it is. So it's somewhere in here, but it's a real particle and it's in a real location. That's the or argument. And they're arguing that somehow they have some reason to say we have to go with and, because when we measure photons in our measurement experiment, our detector experiment, it forces there to be an and, or it can't be the right answer. Yeah, or is still good because their rationale for eliminating it as the right answer is nonsense, is made up.
So So first, if we just use the Schrodinger equation, this beautiful equation that's written down, would that be enough to cause a wave to undergo that kind of transformation? Nice and spread out, and now collapses to one location where the particle is found. Can the Schrodinger equation do that for us? No.
Well, it's kind of silly to say it can't, because that's exactly what it's attempting to do. It's give you the probability. So it's basically giving you some indication that, yes, if you can do the experiment more than once, the Schrodinger equation will give you very good information. So, because you'll have a certain number of collapsing outcomes in certain positions. So it'll tell you what the collapse will be, probabilistic. So here, they're even arguing against, 1 minute it's the perfect equation that tells you everything, next minute it doesn't tell you anything. I mean, it's so duplicitous.
No. That means no, right? It means yes. Okay. So like I said, Gerard has distinct views which are spectacularly interesting. We're going to come to those in just a moment. But let's now follow the history of the subject, where we're going to just follow our nose and we look at the equation we have in it, and it doesn't do it. So what then do we do to get out of this impasse? And to make this impasse even a little bit more compelling, I'm going to take you through one version of this story that I hope will make the conundrum as sharp as it can be, and then we'll try to resolve it. So I'm going to take you through a little example over here where we have, say, a particle somewhere in Manhattan. And let's imagine that the probability wave makes the particle location peak at the Belvedere Castle in Central Park. So that's just randomly chosen. What that would mean is if somehow I had some measuring device that could work out where the particle is.
Right, it's a measuring device that wasn't peaking in some other place, I mean, the fact is that we're not talking about things that have a probability that's a line like this. If it had a line like this, a probability line that's this dramatic, then you'd say, yes, the particle is in a specific location. You wouldn't really have... The fact is, all this other crap wouldn't mean anything about these other possibilities, because, look, it's 99% of the time it's here. So the noise you could eliminate. You can eliminate the 1% without losing too much. You're not sacrificing much by saying, we'll just pretend anything that's not there's one of this 99 is just error, and we'll just write it out. We'll write it out of the story. Then we have a particle in a specific location, and we can do a reliable experiment because it's a pretty reliable frickin' particle. So none of this makes any sense. Like, you don't need any of this. If I had a real world where this is the wave pattern for a particle, I wouldn't have any worries, because I can just negate all of this irrelevant thing and just call it noise.
Is experimentally, observationally, indeed, it would reveal that the particle is at that location, the wave is sharply peaked at that spot, and therefore all the probability is focused right there. That's quite a straightforward situation. Imagine we do the experiment again, and the probability wave has a different footprint. Let's say it's way down there at Union Square. If you follow the same experimental...
So again, this idea that they're doing an experiment, that this has something to do with reality again, what sense does it make? You just did a probability equation, which means you looked at something over a lot of permutations. You rolled the dice a lot of times to figure out what the dice do. And then all of a sudden you say, no, well, I changed what's written on the dice or something. What did you change to create this new huge giant probability in some other location? You have to change something dramatically to change the odds of how the dice are going to turn out. So this is just such nonsense.
Measurement procedure, and you go about figuring out through your observation where the particle is, you find, indeed, there it is, Union Square. The conundrum is the issue that David was speaking to, where we now have a situation where we don't have one peak, but two. Now, it's sort of like the particle is at the Belvedere Castle and in Union Square.
Right, so then it wouldn't be peaked like this, right? Then now this is a 50% chance, and this is a 50% chance, or 49-49, and the rest of this mush, this lake of nothing, is the 2% left over. This is so... What person watching this can make any sense out of this mush?
And that's puzzling, because if you go about looking at the observation, what do you think will happen here? Well, the naive thing is your detector kind of doesn't know what to do. It's sort of caught between the particle is at Belvedere Castle and it's at Union Square. But the thing is, nobody has ever found a detector, well, I should say nobody who is sober has ever found a detector that does this, right? This is not what we experience in the real world. So this...
But we sort of do. We do detect a different outcome. We detect a 50-50 chance. It's a heads or it's a tail. So we do detect what we see there. But yeah, you never detect the coin that isn't either heads or tails. You can't detect it in some state where it's neither heads or tails as a landing coin. A coin can't land as neither. Well, it could land on its edge, but we know we're not playing that game.
This is the issue that we have to sort out, because that naive picture is not borne out by experience. And I think many people here, and many people...
All right, so it's just when he said that, it's not borne out by experience. Yes, it is, completely. Everything in experience says that's how it works. Nothing is ambiguous, really, except the limitations of our perception. But every place our perception is reliably working, that is every place where we can bang photons off of something and it's a solid object and it's not going to be changed substantially by banging the photons off of it, we can observe it quite well. We can see, like human behavior is seldom affected by how many eyeballs are watching, the human behaving, right? That's, or the video camera. There's completely passive ways to watch humans, right, where the video camera isn't doing anything. It's not reflecting more light, it's not doing anything specific to change the behavior of the object so we can see it. And we know there's places where we can't do that. There's little places where that's not possible. But they're saying we're supposed to believe that just coincidentally all the real wacky stuff happens in the very place we can't see. So they're saying, yes, there's no boogeyman in the room, but inside the dark closet there's one. It's just a coincidence. Boogeymen always hide in dark closets. And when you open the door, there's no boogeyman.
The community have thought about this. You, in particular, David, believe that you have the solution. It has a long historical lineage, but why don't you tell us a little bit about the approach that you think resolves this?
Okay, so to start by reminding ourselves, what's the problem with just saying...
All right, so this is the part that's just kind of silly, right? Because he's just pulled this out of his ass, like 1/3 of the physics, and another third of the physics pull something else out of their ass, and the other third pull some other silly story out of their ass. And it's just gremlins versus, what other little pixies versus, whatever, Tinkerbells. Yeah. It's a silly conversation.
That the wave function suddenly jumps to being in Belvedere or Union Square. And the problem is really just that we have to modify the equations of physics at every level to handle that. And
The Schrödinger equation just does not let that happen.
And to put it mildly, we've got quite a lot of evidence for that structure of physics. And for a whole bunch of reasons, actually trying to change the physics to make that sudden collapse of the wave function physical, and not just, as Gerard was putting it, not just a sort of fuzzy talk, is a really, really difficult technical problem. But you could say that we have to do that because, like Brian's saying, it doesn't seem we ever see a particle here and here at the same time. And I think Brian's joke is about right as to what our intuition is about what it would be like to see a particle here and here at the same time. It would be like being really drunk, like seeing double. But here's the thing, if you want to work out what some physical process would be like, and my looking at a particle is just one more physical process, turns out intuition is not a very good way to predict what happens. So how do we ask, what would it really be like to see a particle?
So again, intuition thrown in here as if, that we see a certain event, trains running over watermelons, and so our intuition is wrong somehow. The watermelon's not going to be a mess. There's some magic. The train's going to pop off the track and the watermelon will be spared. There's some reason to believe. No, there's no reason to believe.
Here and here at the same time. Well, what does the physics say? I'm just one more measurement device. And the physics says something like this. If I saw the particle here, I'd go into a state that you might call a seeing the particle here state. If I look at the particle there, then I go into what you call a seeing the particle there state. If it's in both states at the same time, then I go into both states at the same time. So, being a little loose for a minute, then I'm now in the state seeing the particle here and seeing the particle there. And if I tell Brian where the particle is, because I'm sure he's fascinated, Brian's now in the David says it's here and David says it's there. And the whole audience will have to listen to...
Right, so we already know where this is going, right. So there's new universes created every single time some subatomic particle is hit by a piece of force or energy. I mean, I can't even tell, the scale of that, just the surface of my hand. Underneath all the millions of microbes and all the other shit that's on the surface of my hand, it will get smaller, smaller. All those little tiny events are all creating new universes where we're all living in all those universes doing all this minutia over and over and over. Millions and billions and billions. And the only thing that changed is one little frickin' silly left-right decision on the subnuclear level. I mean, when you think, it's just an insanely silly explanation of reality. I mean, it's so much worse than religion. I mean, it's just worse. It's so silly. It's so preposterously, you know, complex in terms of just the logistics of reordering where all the things are in quadrillions of universes of duplication. I mean, you could just, I mean, you know, I'm just saying, you know, just, come on, face bomb. Come on, people. Say no to stupidity. Say no to nonsense. Say no to this fantasy, this fucking fairy tale that's not even a fairy tale. Like I said, Pooh characters would make more sense. Smurfs, talking fish, anything but this crazy talk. Anyway, it's just too stupid. Too fucking... I mean, you saw how bad the evidence was. The logic they're using to justify this terrible, insane jump to non-reality, to this fable, you know, is just so bad. I mean, I couldn't even give you an illustration of a Christian making a mess out of evolution that's more of a mess than they made of the two-slit experiment. Christians are more respectful of known facts than these physicists are, and that's just a fact. And yet I'll get ridiculed, you know, for denying, oh, they're so smart and they're so great and they're so brilliant and they've given us so much and blah, blah, blah. What a pile of crap this is. And you're all falling for it. I mean, you're dupes to it. It's pitiful. It's pitiful. Ludicrous. Life is just ludicrous. I'm sitting here on, you know, they ought to just call it Planet Ludicrous. The more bullshit you speak, the more you get listened to. It's terrible. All right. So anyway, good night. I'm done. Yes, I've run out of will to endeavor to persevere. I should have to explain to you how this is nonsense. And that part of the nonsense is that they're talking about it as if this has something to do with some sort of rational theory when they don't even agree. They don't believe. The most physicists don't believe this horse shit. And he's selling it as if some sort of, this is a reasonable explanation. No, it isn't.